Hello everyone. So in this video we have got for you another algorithm for shortest path, which is Bellman Ford. So let's see the outline of this video. First of all, we will get to know some important terms. Then we will see the pseudocode of it. Then I will explain Bellman Ford algorithm using the graph, its time complexity, and then we will see how this algorithm can be used to find a negative cycle. And then finally we will see the correctness of it. So let us see some of the important terms. First one is tensor edge. It is an edge for which the distance of v is greater than the distance of u plus the weight of their edge connecting them is called an tense edge. Now let us look at edge relaxation. It is lowering the cost to reach any vertex v connected by a tense edge u, v by updating the distance of vertex v to distance of vertex u plus the weight of their edge between them. So let us look some of the variables to keep in order to perform the Bellman Ford. It is only the distance array which will store the distance of any vertex u from the source vertex. So let us see the pseudocode. First of all, I will update the distance of the source vertex to 0 and all the other vertices to infinity. Then I will run this for loop from I is equal to 0 to v minus 1, and then we will look at all the edges present in the graph. If it is tense, we relax it, and this is performed for v times. So now that you have understood the pseudocode, let us see it working using a graph. First of all, I will take A as the root node, initialize the distance of it using 0 and all the other vertices as infinity. Now we have to iterate through all of the edges and see if it is tense or not. If it is tense, then we have to relax it. First of all, I am looking at the edge connecting A, B. The distance of b is infinity, which is greater than the distance of a plus 6. So it is tense, we have to relax it. I will relax it and update the value to 6. Now seeing this edge, which is connecting a, d, it is also tense, updating the distance of d to 1. Now using the edge connecting d, b, which is 1 plus 2, which is equal to 3, is less than the distance of b. Now we have to relax it and update the distance of b to 3. Now the steps of relaxing the tensor edge will repeat again and again till no tensor edge is present in the graph. Now exploring the edge from D to E, the distance of D was 1, and if I move from D to E, it will be 1 plus 1, which is 2, and the distance of E was infinity. So I will relax the tensor edge and update the distance of E to 1 plus 1, which is 2. Moving on, we have a total of 3 edges which are not being explored yet. So if I explore the vertex C using this edge connecting E and C, the distance of C would be the distance of E, which is 2, plus the weight, which is 5, and the total will sum up to 7. So as it is tense, I will relax it and update the distance of C to 7. Moving on, if I explore B from E, the distance of B will be the distance of E, which is 2 plus 2, which is 4. As it is greater than that of 3, it is already relaxed. So only one edge is left, which is connecting B and C. So if I take a path from B to C, the distance will be the distance of B, which is 3, plus the weight, which is 5, which sum up to 8, which is greater than that of 7, which means the vertex C was already been relaxed. So now you can see the distance array have given us all the vertices with their shortest distance from the source vertex, and all of the edges are relaxed. So moving on to its time complexity, as we know that the outermost for loop runs for I is equal to 0 to v minus 1. Therefore, it will run for total of v times, and the inner loop runs for all the edges. Therefore, it will run for e times. And the relaxation of any vertex takes a constant time, as it is just updating a value in the distance array. Therefore, the total time complexity will be E into V. So let us see how we can detect a negative cycle using Bellman Ford. It is just by running the inner for loop again and see if there was an edge relaxed or not. As we know that a negative cycle will contain a negative edge, therefore our algorithm would try to relax the tense edge, which can be detected just by running the inner for loop, which was used for exploring all of the edges once. So let us see some claims through which I will prove the correctness of the algorithm. The first claim states that after the ith iteration, the distance of v would be less than equal to the length of the shortest path using at most I edges. Let us see its proof. Let the number of edges be e. So for iteration number 0, as it is only the source vertex, its distance is 0, and which is also its shortest path using 0 edges. And the induction hypothesis states that after the kth iteration, all the vertices would have the shortest path using at most k edges. Now proving it for iteration k plus 1, let there be a path from u to v which uses k plus 1 edges. As we always check the condition, distance of v is greater than distance of u plus the weight of h between them. Therefore, the distance of u will be the shortest path using at most k edges, and the distance of v will be the shortest path using k plus 1 edges, because k edges will be used by the path from the source vertex to u, and 1 would be the edge which will connect u and v. So now let's see what we have got for you in the next video. So that's it for the course. Now the evaluation criteria as follows, that you have to attempt the final quiz and the passing percentage would be 60%. So that's it for the video. Thank you.